All right, so good evening. We're going to be presenting a comparative study of expansion, deflection, and bell nozzles for enhanced efficiency in rocket propulsion systems. So to sort of start off, we're going to go through a table of contents of what we were presenting today. We're going to start off with what it takes to design a 500-second specific impulse engine, followed by some background, the objective of this research, the literature review we used, the methodology we used in designing our geometry, the results we generated, as well as the conclusion and some references. So to start off, the closest 500-second specific impulse engine that exists at the moment is the RS-25, also known as the Space Shuttle Main Engine. It is actually also being used for the SLS, and it has a specific impulse at a vacuum of 452 seconds, and at sea level, a specific impulse of 366 seconds. Now, the RS-25 is a closed cycle engine, meaning that it does not throw out any other exhaust other than the reactants going through the combustion chamber and through the nozzle. It consists of turbo pumps, which are powered through a turbine, a preburner, a combustion chamber, and the nozzle. The fuel passes through the turbo pumps to increase the pressure and then splits to go around the nozzle to cool the engine. It is then sent to preburners, one for fuel and one for oxygen. Both preburners are fuel rich, and the exhaust of these preburners drive the turbines of the fuel and oxygen turbo pumps and are sent to the main combustion chamber. Part of the fuel and oxidizer is also used to drive the low pressure turbo pumps and also is used to pressurize the fuel and oxidizer tanks. Now, preburners are important because they ease the combustion and make it more efficient. In this case, the preburners help put hydrogen gas and water vapor into the combustion chamber, and the turbo pumps help increase the pressure of the propellants. And when you reach the combustion chamber, you have a pressure of about 207 bar, a temperature of 3,575 Kelvin. You are mixing liquid hydrogen, liquid oxygen, and you have a mixture ratio of 6:1 for oxidizer and fuel. Now, the dry weight is 7,774 pounds, and the max thrust you can produce is approximately 512,000 pounds. Now, to help design this 500, to give it an idea of how to design a 500 specific impulse engine, we used a rocket propulsion analysis software, and using the same mixture ratio of hydrogen and oxygen and maintaining the area ratio of 69 between the throw and the exhaust. And it was said that we had to pre-burn the hydrogen and oxygen temperature to about 3,000 Kelvin, raise the chamber pressure to 500 bar, and raise the chamber temperature to 3,790 Kelvin. Now, even through all this, we were only able to achieve a specific impulse of 475 seconds, which means we need to find an alternative to increase ISP other than pressure and temperature changes. So a little bit of background about the analysis we will be doing. So a nozzle is defined as maximized thrust by efficiently converting the high pressure, high temperature exhaust gases into high velocity exhaust streams. So a basic diagram of a rocket nozzle is shown on the top left. Basically, we have stagnation pressure and temperature in the combustion chamber. And assuming we don't have any significant pressure changes or temperature changes or velocity values between the end of the combustion chamber and the beginning of the nozzle, we can assume that the pressure and temperature of the combustion chamber are at stagnation, and also are at same stagnation values when entering the nozzle. And so then the gases pass through the throat where they accelerate to Mach 1, and at these supersonic speeds, they accelerate even further due to the diverging section of the nozzle. And they will accelerate to a specific pressure at the exhaust and velocity as well as temperature. And depending on how these pressures and temperatures compare with the ambient conditions, can help us understand the performance and efficiency of our engine. Now, one of the variations of rocket nozzles that we chose to analyze, this was called the expansion deflection nozzle. Basically, what this means is that flow is deducted by a plug and is forced to stick to the nozzle walls. And the presence of a free jet boundary to the expansion process lends a kind of self-adjustment to back pressure variations. Basically, what it's saying is that the way that flow behaves as it moves through the nozzle is dependent on how what the ambient conditions are. And it's found to have shorter length with similar efficiency. So a lot of weight reductions can be put in place and help ease the design of the rocket. And also operates in two modes, open wake and closed wake. Basically, open wake is when you have the blue region that is at a higher pressure that reaches the exit of the nozzle, and then it starts to close as you move higher, as your ambient pressure starts to decrease more and more, until eventually it forms what's called a closed wake. And basically here, the turbulence often seen in the wake region is isolated, and then we also introduce what's called the effective area, which basically means that the thrust that you will be calculating will only be used depending on the area that sort of isn't highlighted in the yellow region right there. And so as the wake closes more and more, this effective area starts to increase, and therefore you can increase your effective exhaust velocity and other parameters because of this closing.
So the objective of this research is to determine whether the expansion deflection nozzle can actually lead to a better design for a 500-second engine. And so we've decided to pull this component out because it appears that this is one of the easier components to change and implement and get an instant response and efficiency metrics. And so what we're going to do is we're going to compare the expansion deflection and bell nozzle performances for both a vacuum and then the expansion deflection nozzle at sea level. And we're also going to investigate the effects of our specific pintle design.
As far as literature pertaining to the expansion deflection nozzle, one of the first analyses done was by Robert Wasco in a 1960s NASA report. So Wasco determined the nozzle actually was not as efficient as expected, and in fact, it was just as performant as actually less performant than a conical nozzle at sea level and vacuum. It was not altitude compensating, whereas a plug nozzle was. Noting that it was only operating in closed wake, which would explain that poor performance and lack of altitude compensation. However, in 2002, Taylor published his dissertation providing an exploration into different expansion deflection nozzle contour designs. And in particular, he talked about the works of Wasco, Rao, and Weller. So Wasco and Muller use very similar nozzle designs, as you can see at the bottom two in the picture there. They have a very low throat angle, and they use an ideal contour. And both of these nozzles operate in closed wake mode. They are not very efficient and do not provide any altitude compensation. So Taylor makes note that it's not surprising that in his analysis, Wasco found that it was not performant and it was not altitude compensating. So in fact, he referred to the geometry as just peculiar and not allowing it to operate in open wake mode. Whereas, sorry, can you go back previous slide? Yeah. The route type nozzle with the rounded pintle and the optimized contour would allow for operation in open wake. So in particular, what the criticism Taylor had for the Wasco geometry was the low pintle separation angle. It was even lower than that of Weller's geometry, which is why it was very peculiar. The throat was also considerably upstream from the point of separation, and all of this resulted in a decreased open and closed wake base pressure. And overall, due to the fact that the Mueller nozzle was not intended to operate in an open wake mode, it's not surprising that the Wasco nozzle only operated in closed wake and was not performant or altitude compensating. So it kind of casts doubt on the notion that expansion deflection nozzles are not performant or cannot be performant. And in his dissertation, he talks about optimizing the contour to actually get it to operate in open wake and provide that altitude compensation. So yeah, I said before, Rao is one of the design philosophies for the expansion deflection nozzle geometries. So in particular, Rao utilized his established bell length optimization. So you could possibly reduce up to like a 50% decrease in length. So that could present a reduction in mass of the nozzle. He made use of a much larger throat angle, about 75 to 90, all the way up to 90, which was much higher than that of the Mueller or the Wasco nozzles. And overall, what this would allow for is a longer operation in open wake mode. And it is critical that this happens because the expansion deflection nozzle needs it to operate in open wake for there to be altitude compensation.
So our geometry methodology this is kind of our overview. And so what we did is we mathematically designed our nozzles in MATLAB and we sketched them as a contour. And then those contours in MATLAB were imported as a collection of points into SolidWorks, where then we could mold the model, scale the model to its appropriate length, units, and then we will mirror it to get a full planar nozzle. And so that's where we went different with typical research. A lot of previous research did asymmetrical CFD when we're doing a full nozzle CFD. And then we created a mesh for this full nozzle in the ANSYS workbench. So for our exhaust contour, what we did is we did a thrust optimized parabolic nozzle, which is a quadratic Bezier curve. And so here it's shown from Rao, and this is actually, he approximated this. And as you can see here, here's your throat, and then you come up in this endpoint is your theta n. This is your angle going into the curve, and then your theta e is your exit angle. And so what he found from this actually is an 85% of your length of a bell nozzle provides a 99% of your nozzle efficiency. And so we took that metric. And so here's our equations that we generated our curve with. We know n points because we know the throat exit. And then we know E from the length approximation given by Rao, and then our throat area that we chose. And so the M here is defined by the tan of our angle going into N. And then M2 is our tan of our exit angle. And then using these equations, we can generate a curve. And so here's our bell contour design. As you can see here, the blue is our our converging section. And then it goes into our diverging section. And so our area ratio for the bell contour is 26.5. The radius is 0.0254. Our exit theta is 4.5 degrees. The length of the whole nozzle, the length from the throat on is 0.3932. And then we have an exit radius of 0.1150. And the design Mach is 3.6. So next, here's our mesh. And this is created an ANSYS workbench, has around 9,000 elements, 59,000 nodes. It's quadratic elements. Our skewness or our quality was 0.75. And our element size is 0.002 meters. And then for the expansion deflection design, this was a little more complicated. This image is taken from Taylor's dissertation. And this is where we also took our optimal design, as we looked at his graphs of thrust coefficient for different radius of the pintle, radius of the walls, and these entry angles. And that's how we designed ours. And so the area ratio for our ED nozzle is also 26.5. The throat angle here is 45 degrees. The radius of the pintle and the radius of the wall is equal to the throat radius, which is 0.0254. And then our entry angles here and here are both 15 degrees. And then, of course, the exit radius is the same as the bell, and our throat radius is the same as the bell. But as you can see, our nozzle length is slightly shorter than the bell nozzle. So here's a contour for our expansion deflection nozzle. As you can see here is the entry to the throat. And the throat occurs around right here. This is the two closest points. And then we have our same exhaust optimized approximated contour here. So here's the expansion deflection mesh. As you can see, it's 28,000 elements, 86,000 nodes. Again, all the exact same parameters as our bell nozzle, essentially. Next, we're going to move on to our methods overview. And so our CFD was ANSYS Fluent, and we did a density-based 2D solver, which is the standard for, supersonic. Our chamber conditions were 300 bar at 3000 Kelvin, which is very similar to a Raptor engine. For our fluid medium, in order to compare it to other works, we used air like they did as an ideal gas, and we used the Sutherland viscosity. And our viscous model was the SST K omega with an inlet turbulence of 5% with a turbulence ratio of 10. And so that introduces a little bit of turbulence into the model. So here is our CFD parameters. And so as you can see, we have our operating pressure at 0 pascals, inlet pressure at 300 bar, 3000 Kelvin, with our outlet pressures at 0 for vacuum and then sea level, and the same for our temperatures. And quick mention, we ran 1,000 iterations max, or for the bell, when it converged early, we stopped it early.
Right, and so here's our bell contours we got using ANSYS for vacuum. So as we can see here, we have the just a standard bell. There's nothing strange to see here. We have a uniform acceleration throughout the entirety of the bell. We can see the shocks forming initially there on the left side, and then meeting to form those on the other side. And then on the next slide, we'll have the static pressure and velocity. So static pressure is going to be higher at the boundary layer, as seen in the graph, and then the peak on the left side there is going to be the area between those shocks. So then you'll see those the peak and velocity on the right side as well. Those are where those shocks are as well. You'll see that in the mock pressure graph on the next slide. And yeah, you can see those peaks there as well.
So here are expansion deflection contours, and these are for a vacuum. And so if you take a look at this top left, we have our mock contour. You can see the flow comes in, hits the throat right here, and then as it's expanded into here. And so there is a shock coming from the flow being pushed into the wall here. And this area right here is our non-circulating region. And so this is, basically stagnant flow. And so when this flow expands and hits this stagnant flow, it actually forms some turbulence, as you can see in this image. And the way we know this is a closed wake is you can see this turbulent energy come together and it's combined. And we also see this here, how these shocks will meet, and this flow actually has some velocity. And so here's our sea level contours for the expansion deflection. And I'm going to move very quickly in between these so we can see some differences. So in the top left, we can see a greater expansion in the vacuum than the sea level. And that is, of course, because our outlet parameters, our pressure is higher for sea level. And then at the bottom, the turbulent energy, you can see there's still a blue line of non-turbulence. And so this is essentially, it's very, very close to closed wake, if not closed right at the exit. It's very close though. And then here you can see our, basically our shocks in this tube. And the difference between these two is this shock exits the tube before it hits the wall and the vacuum. And the next, we're gonna look at our pressure plots. And so here's our pressure, static pressure specifically for our vacuum. And this increase in pressure is our stagnating flow that we'll show later in this velocity. There's not a lot of velocity here. And then here, these peaks are our shocks up here. And we'll show that in a later diagram. And then, of course, the temperature, that hot non-circulated region is a lot higher. And then here's our kinetic energy for a vacuum. So this is a very, very turbulent area coming out of the very center of it. And you can see this velocity drop. Now it's not to zero, but it's a drop of 50% to 1,000 meters per second. And then finally, here is the Mach diagram for the vacuum. As you can see, there's a massive Mach drop, but it doesn't go below zero. It's still supersonic flow. And then next are our plots for sea level. And so these are very different, especially in the pressure region. As you can see, there's a massive decrease in pressure at the very, very tip of it. And there's also these high peaks from the shocks, but we don't get that same curve from the vacuum. And then the temperature, you can see this little in between where it's still slightly open wake. And that's shown here with this kinetic energy, it's open. And then here's, of course, our velocity dip, which is greater at sea level. This goes down to 800 versus 1,000. And then here's the Mach plot. So here's the comparison side by side to kind of see the shocks and the pressure and how they interact. And so here you can see this shock is this point, this shock is this point. We have this not stagnant, but slow region that has a massive increase. Versus over here, you have this shock, which lines up here, this shock that lines up here, and this peculiar point where we believe that this is resembling a slightly open wake, this massive pressure drop. And it's a very small, it's hard to see, but that's what we believe that is.
Okay, so now we are going to conduct a quantitative comparison of the different performance values of the two nozzles at the various ambient conditions. So we created these two tables that kind of highlight the different values we generated as well as the calculations we made. So the first thing I would like to point out is that effective area of the expansion deflection nozzle increases with altitude. So the first two columns are vacuum, sorry, the first two rows are vacuum and the last two rows are sea level. And if we look at the expansion deflection effective area, we start off at about 0.0323 meters squared, and it increases to 0.039 meters squared. So we can see that there is actually definitely an increase in the effective area with the altitude. And this was achieved using a shorter nozzle. So if we look at the effective area of the bell, it stayed pretty much the same, whereas and had a longer length than the expansion deflection nozzle. So this provides evidence that by using these expansion deflection nozzles, we can get better. We can start getting better performance of the flow at shorter nozzle lengths, which we can then use to reduce weight. Now, we also have in the second and third column the pressure at the exhaust and the velocity at the exhaust. Now, if you remember back in the plots, it seemed to be extremely noisy, and therefore you may ask, how exactly did we generate these values? Well, a lot of the peaks, not only did they were they as a result of shocks, but the variation between them actually seemed quite linear. And so if we were to take the average of those two linear sections of both pressure and velocity, we see that in the effective area region, they actually seem to meet with the values of the non-shock affected parts of the effective area, which gives us confidence in that these values are more accurate in approximating the parameter flows at the exit of the nozzle. So looking into the expansion deflection at a vacuum, we get a exhaust pressure of about 500,000 pascals, whereas at sea level we have 850,000 pascals. So with this increase in effective area, we actually get a much bigger drop in pressure. And this is further reflected in the velocity, where at a vacuum we have 1,990 meters per second. And in the expansion in the sea level, we have 1,950 meters per second. You can also see that the flow parameters of the bell did not change at all. So this just gives in more confidence in the fact that this expansion deflection nozzle is in fact behaving the way we would like it to. In the bottom table, we now can plug in these values and calculate our performance. So the mass flow rate is in kilograms per second, and these values were actually given to us by ANSYS. So we didn't actually plug them in for boundary conditions. However, we can see that the ambient pressures is 0 pascals for the vacuum and standard sea level values for the bottom two rows. And if we calculate the effective exhaust velocity, we see that at a vacuum, we have an effective exhaust velocity of about 2,000 meters per second for the expansion deflection, and at sea level, 1,972 meters per second. So plugging these two values into the specific impulse equation, we get a specific impulse of about 204 seconds at a vacuum and 200 seconds at sea level. So we can definitely see an increase in specific impulse with altitude. Now, as the bell, the effective exhaust velocity at a vacuum is 1,997 meters per second, and at sea level is 1,994 meters per second. And so the specific impulse change is actually very, very low, because velocity is in fact the most dominant term in the effective exhaust velocity equation. Therefore, because both of their velocity values at sea level and a vacuum are the same, we don't get that much of a higher specific impulse increase. So now looking at the actual percent difference to get a better comparison, we see that the expansion deflection specific impulse between a vacuum and a sea level increased about 1.78%. And the variation of this specific impulse is not as high as expected, but it does demonstrate the larger increase in specific impulse of the expansion deflection nozzle versus the bell nozzle, because from sea level to a vacuum, we get as you go from compare vacuum and sea level, you get a 0.18% higher specific impulse in a vacuum for the bell nozzle. Now, one thing we would like to point out is that the specific impulse of the expansion deflection nozzle surpasses that of the bell, because at sea level, we start with a lower specific impulse for the expansion deflection nozzle of about 1.1%. Whereas once we reach a vacuum, our specific impulse in the ED nozzle is about 0.5% higher. So another thing to point out is that these percent differences across the board when comparing the bell and the ED nozzle, we see that the specific impulse of the ED is able to keep up with that of the bell. So even though the design is different and the flow behavior is different from sea level to a vacuum, it's still, the ED nozzle still generates values that allow the specific impulse to keep up with that of the bell. And we can further be more confident in this because even though the ED is not optimized, it already does demonstrate superior performance than that of the bell. So I'm going to talk a little bit about application as well as how we can further apply this work. So the first is that we must conduct a further investigation in how to identify optimization techniques of the expansion deflection nozzle diverging section. And what I mean by this is that because we use the quadratic Bezier curve to have boundary conditions that match that of the bell nozzle, it basically became more horizontal than we would have liked, which means that the effective area was not able to increase as much as we could potentially see had it been had the nozzle been a bit wider. So further investigation is required to basically identify how the behavior of the effective area changes as a result of a wider or shorter nozzle for the ED, as well as how we can control that change in effective area as in terms of also how long the nozzle actually is. Now, another thing we proved in this study is that the use of the molar pintle will not generate the increase in specific impulse due to the turbulence it generates and the closing of the wake. So as we mentioned before, at sea level, we have a almost closed wake caused by the basically how almost vertical the expansion fans are in the molar pintle, and basically this closes the wake prematurely, so we are not able to really be able to control the wake. And so because of also the turbulence it generates, we can also not measure too well how much we can optimize the performance of the nozzle. Now, because the pintle is essentially feeling stagnation temperatures coming from the combustion chamber, its material is one of the main obstacles for designing these nozzles, because if you choose a material that is highly resistant to heat transfer, you could throw away that extra weight loss that you got from the length of the nozzle because of this choice in material that could increase the weight, and you can lose some of the performance you initially gained by this type of nozzle. And also the variation of the fuel type they use on these engines can influence the exhaust velocity values as well as the flow parameters that the pintle can feel. So if you remember from the velocity equation, it's proportional to the temperature you get from combustion, but it also means that if you get a higher or lower combustion temperature, you will also be changing the stagnation values that the pintle will experience. So depending on how you design, which fuel type you use will also impact the design of your expansion deflection nozzle, the design of your pintle for the expansion deflection nozzle. So in conclusion, we would like to describe how this study proved that design of the pintle is very important, and by being able to have a more round pintle rather than the one in the molar where it's sharp, we can essentially control how the wake closes and therefore take more advantage of that altitude variation of the effective area that we would like to be able to experience with these types of nozzles. So with that, I would like to show the references here of the ones we use for this project, and I'd like to thank you for your attention.